All right, so here we are back at the combined gas law. So standard temperature and pressure, STP. The temperature is set at 273 Kelvin. That's the number you need to remember to convert to Kelvin, so it's a good thing to remember it as well as the standard temperature. The standard pressure is 1 atmosphere or 101.3 kilopascals or 760 millimeters of mercury or 760 torr. Whichever one of those goes in is the one that comes out for this. Make sure that all the units and pressure match. Don't mix and match in the same problem. You can mix and match throughout all the problems, but don't mix and match in one problem. So for example, if you had to convert 123 kilopascals to atmospheres, I think we did this already, but I'll just do it real quick. So 123 kilopascals, you got to get rid of kilopascals and you got to go to atmospheres. And so you find that conversion right here. These are equal. So that means that 101.3 of these equals one of those. And when you do that, I believe it was 1.2 atmospheres, if I'm not mistaken. So that is, yes, 1.21. That is that. And the combined gas law works for when the amount of gas is held constant. So you're not messing with the amount of gas. P1 V1 over T1 equals P2 V2 over T2. So when does the gas not change? When you have something like a bubble or a balloon or a syringe that goes from cold to hot. That gas syringe, this thing that seems to happen all the time in science based on this unit. So you have a gas syringe in a cold situation, then you bring it to a hot situation. And that is when you use the combined gas law. So the amount of material inside doesn't change. And I think I still have, let me see if I still have my thing running. Discard that for now. Yes, I do. So when the amount of gas does not change, this is when you use it. If I change the amount by letting some out or putting more in, now the P1 V1 over T1 equals P2 V2 over T2 does not work. So we only use that when the amount does not change. So moving on. So here they are. Remember, temperature's always got to be in Kelvin. Volume should be in liters. And pressure should be the same unit. I say should be in liters. You can actually pull these off with milliliters, but for the next thing with the ideal gas law, you cannot. So the key to these problems is understanding what state 1 is and what state 2 is. So a sample of gas is originally at a pressure of 3 atmospheres. So you should, let's go back to pen. So you should make sure you look at pressure 3, temperature. Hopefully they'll all be together like this. So that means those three things are in the same state, right? A gas is originally at pressure 3 atmospheres, temperature 293 Kelvin, and volume 318. So the P1 is 3, the V1 is 318 liters, and the T1 is 293 Kelvin. Heated to a temperature, so your next temperature, I will change colors because I can. Temperature of 270 or 323, pressure 250. So we have two things in state 2. We do not have a V2, so that's what we're looking for. So your P1 would be 3. Oops, let me change that back to red. So your P1 would be 3, your V1 is 318, and it's divided by your T1, which is 293, and that will equal your P2, which is 2.5. Your V2 is what you're looking for, and your T2 is 323. So then what you can do is either turn 3 times 318 into a number and then do some cross multiplying. So 3 times 318 would be 3 times 318, 954. So then that would be 954 over 293 is equal to 2.5 V2 divided by 323. And then you can do some cross multiplication here if you wish, or you could just turn all this into a number and all of that to a number and solve for V2. Whichever you're more comfortable with algebraically, you should get an answer of 420 liters. So next sample question. So a volume of gas occupies a volume of 895 liters. So our V1, actually I should erase that because I think I already do this. So our V1 is the 895 STP, we talked about STP is temperature of 273, and pressure can vary from 1 atmosphere to 101.3 Kelvin to 760 torr. Since this next pressure is in torr, it might be a nice idea to use the 760 torr then as your P1 and your T1. And this would be your V1. And then your P2 now is that 1277 torr, and your T2 is what we're looking for, and your V2 is 574 liters. So I've made these first two problems that you could do on this interactive. You could actually get these numbers if you want to try. Let's keep that for now. If you want to try to do it here, the way you do it, if you reset it, I'm pretty sure that I just had one pump of yellow gas in there. It might have been two. And I think you can get those situations. So if you want to do 760 torr, and which is 1 atmosphere, and 895 liters, I'm pretty sure this bad boy will go up to 895 liters. If you want to just really see what it is we're doing, but you will see, look at that, pretty good. So 895, or not, 885, 892, one more, 899, 892. I guess not. All right, well, you can play with it that way if you want. Let's get back to this. Boop. All right, so the point being, you got to get your P1, V1, and T1, your P2, V2. Then it's just a matter of putting them into the equation. So this would be 760. Sorry about that. 760. 760. All right, so 760 P1, V1 is 895 divided by T1, 273, is equal to P2, 1277, V2 is 574, and that's divided by T2. And we're solving for T2. So again, you want to make these a number, and these one number, and then cross multiply at that point. After you get those as numbers, you're going to have to practice some algebra, but you should get, let me try that real fast. So 760 times 895 is a huge number, divided by 273. So that's 2491. So this is 2491 is equal to, and 1277 times 574 is a huge number, 7329, 732998 over T2, So then you multiply T2 over to the other side. So it comes out to be this divided by 2491. Is that what that nastiness is? And you get a temperature, T2 is equal to 294 Kelvin. That's your answer. All right, that was hideous, but that's the way it goes. All right, so example 3. Now we talk about gas has a pressure of 0.25 atmosphere at 65 Celsius. Once you see that Celsius, hopefully you realize we got to go to Kelvin. So that's 65 plus 273, which is 8 and 13, 338 Kelvin. And if the volume is held constant, what is the new pressure if it cools to 45 degrees Celsius? We got to make that Kelvin. So 45 plus 273 becomes 318. So the key here is notice that your volume is held constant. And when your volume is held constant, it's the same as algebraically, it'll cancel out. And if that makes you nervous, that if you have P1, V1 equals T1 over T1 equals P2, V2 over T2, but since V1 and V2 are equal, they would cancel. So you just get rid of them. If you don't like that, since it's held constant, just make them 1. So it's P1 over T1 equals P2 over V2. You can determine what the constant is, and then you can make it 1 liter. So this becomes 0.25 atmospheres divided by 338 is equal to P2, which is what you're trying to solve for, divided by 318. And if you do that, cross multiplying, 0.25 times 318 is equal to 79.5. And then that's going to be divided by 338. And P2 becomes 0.23. So P2 equals 0.23. All right, so that is that with these, and then we get into ideal. Oh, wait, no, we don't. Let's go with these real quick. So Boyle's law recognizes that if temperature is held constant, then temperature goes out, and so P1V1 equals P2V2. And the pressure and volume, therefore, would be directly proportional. So what's this saying is these equal a constant. And since they equal a constant, as P goes up, V has to go down. And if you remember back when we talked about M&Ms, and I'll talk about that in the next presentation, that means pressure. If the amount of pressure is going up and it's still going to equal the same number, that means the volume has to go down to account for the pressure going up. Same with if the volume gets bigger, the pressure has to go down if it's still going to equal the same number. Charles's law, that V1 over T1 equals V2 over T2. So if volume goes up, temperature has to go up for them to equal a constant. You should also, and same with pressure and temperature, the better way, in my opinion, to deal with this is, let's discard those for now, is to again play with this. So if volume is constant and you heat it up, what happens to your pressure? You can see your pressure here is going up. All right, so as the temperature goes up, the pressure goes up. If you cool it down, you see that as the temperature is coming down, the pressure is going down. So those are directly proportional. If you hold the volume and you make it come down, so the volume's going down, you can see the pressure goes up as the volume comes down, and then that's more collisions happening because there's less room for them to bounce around in. And as you increase the volume, the pressure goes down. So the volume's going up, the pressure's going down. There's less collisions occurring for that. And then the last one would be constant pressure. Volume's effect on temperature, which is a little harder to deal. Oh, constant. Yeah, no, it isn't. So it just happens like this. So when you heat it up, the pressure is staying the same, but the volume, because these are getting more energy, they're bouncing around more, they're pushing this up. So the volume's going up with the temperature. Likewise, if we cool it off at constant pressure, now the volume's going down and the temperature's going down because these are slowing down and it's harder for them to keep this piston up. So this all works with this interactive. So that's what I would recommend you do to understand these laws. I won't ask you the names, but you should understand the relationships.